Welcome to another physics class. During our last lesson, we started the topic simple harmonic motion. When we have our last class, we discussed about general equation of simple harmonic motion. Number one, that angular velocity or frequency is equal to 2 pi f. 2, that period of simple harmonic motion t is equal to 2 pi over angular velocity. Number 3, we talk about the displacement of simple harmonic motion from the equilibrium position as a sine theta, where theta is equal to omega t. Therefore, displacement now will now be equal to a sine omega t. Number 4, we talk about acceleration of simple harmonic motion as a is equal to minus omega square s. And since s is a sine omega t, we now have our a equal to minus omega square s a sine omega t. And by then we said A will be maximum when x is equal to a, and this one will occur at the extreme point of the motion, or at the end point of the motion. Then after that one, we look at the velocity of simple harmonic motion v equal to omega into square root of a squared minus s squared. And we said this one, when we have maximum velocity of simple harmonic motion will occur when s is equal to 0, and this one takes place at the midpoint or middle of the motion, midpoint of the motion. So therefore, the maximum velocity of simple harmonic motion v maximum will be equal to omega a. Again, note, we use all this formula to solve some example. And if you want to enjoy the class more, please, if you are just joining us for the first time, or you are with us, you have not subscribed, please try to like, share, and subscribe so you can get the notification anytime I upload a new video. Now, today, we want to look at examples to illustrate simple harmonic motion. Example to illustrate simple harmonic motion. And we are going to, out of many examples that we mentioned, under examples of simple harmonic motion, we are going to look at majorly 3. 1, simple harmonic motion in a suspended simple pendulum. 2, SHL in a loaded spiral spring. Oscillating vertically. 3, simple harmonic motion in a loaded test tube placed on liquid oscillating vertically So we are going to use these three examples to illustrate, to explain simple harmonic motion. Under each example, we are going to look at the following. A, the restoring force, F. B, acceleration of SHL in each example. C, angular frequency of velocity. Number D, period T of each. Number E, we are going to look at the velocity of SHL in it. And finally, F, we are going to look at energy in simple harmonic motion. The first thing we are going to look at is simple harmonic motion in a suspended simple pendulum bob. From the diagram on the board, this is the pendulum bob as it's oscillating to and fro, from this point to this point, back to this point. Now, let's say this is the weight of the bob, and the first thing we are going to look at is the restoring force, which is F. Now, from the diagram on the board, take it as a right angle triangle. Now, this is the weight, this angle theta, and here is the restoring force. That is, at its move, the force that will return it to its equilibrium position. That's what meant by restoring force. I take it again. Restoring force is the force that will return the pendulum ball to its equilibrium position as it's oscillating to and fro. So from the diagram on the board, if you look at it together, you can now see that this place is opposite, while this place is hypotenuse to this angle. This angle 90 according to the diagram. So from there, we are going to have sine theta will be equal to opposite over hypotenuse. That is F over W. So from there, we can now say F will be equal to W sine theta. And since this one is a restoring force, so it will move in opposite direction of the motion of the pendulum. So our F now will be equal to minus omega sine theta. Note that, minus W, note that W is equal to mg. Therefore, we can now have the magnitude of the restoring force as F is equal to minus mg sine theta. That's the restoring force for simple pendulum. Next thing is acceleration of simple pendulum. From the diagram on the board, the accelerating force accelerating force F is equal to ma. That is the force that will accelerate the pendulum to move toward the equilibrium position and back to display as it moves to and fro. Therefore, since this one is force and this one is force, if you call this one equation 1 and this one is equation 2, if you now equate equation 1 to 2, equating 2 to 1, then this one will now give us ma is equal to minus mg sine theta. Then from the equation on the board, m will cancel m, so we have a is equal to minus g sine theta as acceleration of suspended simple pendulum of suspended simple pendulum undergoing simple harmonic motion. Now note, theta is equal to angle of displacement. And theta is very negligible. If theta is very negligible, when the pendulum is being displaced, then it can be removed. So we can have the diagram like this as so we want to consider the length of the pendulum now. This is the length of the pendulum. This is theta, and as it displays from the equilibrium position, this is our x. That is displacement from the equilibrium position. So looking at it from this side, we are going to have sine theta will be equal to x over, that is opposite over hypotenuse, x over L. So if theta is negligible, then it can be removed by replacing it with this x over L. What we have as A is equal to minus g sine theta, so we can now say our A now is equal to minus g s over L, since our sine theta is equal to s over L. So in simple, we are going to have A is equal to minus gs over L. Now, don't forget, s is what? Displacement. S is equal to displacement, that is from the equilibrium position. Now, recall that from general equation of simple harmonic motion, A is equal to minus omega square s. If that is the case, compare these two equations now, this one and this one. Then we are going to have minus omega square s will be equal to minus gs over L. Then minus will cancel minus, s will cancel s. So we are going to have omega square will be equal to g over L. So therefore, omega will be equal to square root of g over L. Don't forget, the omega now is the angular frequency of velocity. Angular frequency of velocity of the simple pendulum performing simple harmonic motion. forget, the minus here indicate that the minus here and here indicate that the acceleration, as we explained in our former lesson, is directed toward the equilibrium position or a fixed point. The next one is period of oscillating simple pendulum. Period of oscillating simple pendulum. That is, the period is denoted by capital T. Now, recall that from general equation of simple harmonic motion, capital T is equal to 2 pi over omega. And from what we just finished, omega is equal to square root of G over L. To substitute for omega there, we are going to have 2 pi over square root of G over L. Then we are going to have T now will be equal to 2 pi into square root of L over G. If you take the square root of both sides, we are going to have T square is equal to 4 pi square multiplied by L over G. So we are going to have T square is equal to 4 pi square over G L. From the equation on the board, we can now write out the properties of period of simple pendulum oscillating, period of simple pendulum oscillating in SHL as 1. One does not depend on mass of the pendulum bob. 2, it depends on the length of the bob. 3, it depends on the acceleration due to gravity. G. On graph now, if we plot the graph of T square versus L, the graph will be a straight line graph, starting both axes from origin 0, 0. That is, when you have something like this is T square in second square and L in centimeter. So the graph will start from origin 0, 0. Now, the slope of the graph, the slope S of the graph is equal to 4 pi square over G. So from there, the value of acceleration due to gravity can be calculated as S is equal to 4 pi square over G. Therefore, our SG will be equal to 4 pi squared. Therefore, G will be equal to 4 pi squared over S, where S is what? Where S is slope of the graph. Now from the equation again, that is t squared, it means if 4 pi squared over G is a constant, that is 4 pi squared over G, 4 pi squared over G is a constant. Then we are going to have t squared can be directly proportional to L, where our t squared will be equal to KL. Then our K now, which is constant, that is the value of 4 pi squared over G, will be equal to t squared over L. Now, if this thing is put into experiment, we can have series of t and L. So it can be, K can now be equal to t squared 1 over L1 equal to t squared 2 over L2 equal to t squared 3 over L3, depending on the number of times the experiment is being performed, since K is a constant. Next thing is velocity of an oscillating simple pendulum board. Now, from the diagram on the board, we want to consider the velocity. We need to note the energy at each point. Let's call this point as point A, B as the equilibrium position, and this is point C, the extreme point. If the pendulum starts to oscillate at this point, then at this particular point, the energy here will be potential energy. And the potential energy will be equal to mgh, as we know before. As it oscillates through the equilibrium position, when it gets to this place, the potential energy will be converted to kinetic energy. That is Ke, which will be equal to half mv squared at this point B. When it moves to the extreme point, the kinetic energy here will be converted to Pe again. So Pe here again, that is half mv, mgh. So as it's oscillating to and fro, potential energy will be converted to kinetic energy, from kinetic energy to potential energy, all along like that. Now, to comply with law of conservation of energy, we state that energy can be transformed from one form to another, but the total energy remains the same. Therefore, we can now say, apply law of conservation of energy. I'm going to have PE equal to KE equal to KE. Therefore, PE will be equal to KE. Equation on the board, the magnitude of potential energy is equal to magnitude of kinetic energy. Then we are going to have mgA will be equal to half mv squared. From the equation, m is the same throughout. Then we are going to have gh equal to half v squared. Therefore, this one will now give us 2gh is equal to v squared. So v now will be equal to square root of 2gh. Mind you, our h is equal to x, which is equal to displacement. And this one will now show the maximum velocity of an oscillating simple pendulum. Maximum velocity of an oscillating simple pendulum bulb. We said H is equal to S. We can now say V maximum will be equal to square root of 2gs. Don't forget, G is acceleration due to gravity, S is displacement. Find the energy conserved in an oscillating simple pendulum now. That's the energy in an oscillating simple pendulum bulb. So we know we've said already P is equal to K, which is equal to half mv square. And mind you, we said V for simple pendulum bulb oscillating will be equal to, now say, but V will be equal to square root of 2gs. Remove V here, then we are going to have K, that is the maximum kinetic energy of an oscillating simple pendulum will be equal to half m. Then our V square, that will be square root of 2gs into square again. Then we are going to have half m into 2gs. Then 2 will cancel 2. So we are going to have the maximum kinetic energy of simple pendulum equal to mgs, which is equal to PE. From there, you can now say that truly the law of conservation of energy obey. K is equal to mgf is equal to PE. That's where we are going under simple pendulum oscillating to and fro. Take this one as the first example. Under simple pendulum oscillating under simple harmonic motion. The period of oscillation of simple pendulum is 2.15 seconds. Calculate the time to complete 50 cycles. B. Length of the pendulum bulb. C. Angular frequency. And D. Acceleration during oscillation if displacement is 0.13 meter and G is given. G as 10 meter per second square, then pi as 3.142. Now, solution. From the question number 1, we have to calculate time taken for 50 cycle or 50 oscillation. And you know that the relationship between period and time taken, period, T is equal to, that will be T over N, according to this question. And what is our T? We have to calculate T. So make T the subject of the formula, then we are going to have T is equal to T multiplied by N. So this one will now give us 2.15 multiplied by 50. T now is equal to 107.5 seconds. Question B asks us to calculate the length of the pendulum bulb. So we have T is equal to 2 pi into square root of L over G. Take the square of both sides, we are going to have T square is equal to 4 pi square into L over G. Now, make L the subject of the formula. By crossing multiply, we are going to have t square g is equal to 4 pi square L. Therefore, L will be equal to t square g over 4 pi square. Now, the period given in the question is 2.15. So that would then L will be equal to 2.15 square multiplied by 10, then over 4 multiplied by 3.142 square. Therefore, L will be equal to, the numerator will give us 46.23 divided by the denominator 39.49. The answer for the length of the pendulum will be equal to 1.170 meter. That's the length of the pendulum ball. C question, angular frequency. That's square root of G over L. And our G is given from the question. This one will now give us square root of 10 over the value of L, which is 1.170. Then omega will be equal to, this one will now give us square root of 8.55. And the final answer for this one will be equal to 2.924, 2.924. And the unit of angular velocity will be rad per second. The last question under it is acceleration. That is question D. A is equal to minus gs over L. And don't forget, the minus just indicate the direction, that it is toward the center of the circle. So we are going to have our A now will be equal to, the value of this one is 10, S that is given 0.13, then the value of L we got here 1.170, then A will be equal to, this one will now give 1.3, then divided by 1.170, A will be equal to 1.111 meter per second square. That's for question number 1. Take this one as example 2. The period of oscillation of a simple pendulum is 2.0 seconds when its length is 1.01 meter. Calculate the length of the pendulum when the period is 3.4 seconds. Now, solution. From what we have learned before, now the period T1 is given. T1 is given as 2.0 seconds when the length is L1 is 1.01 meter. Then we have to calculate the length when the T2 is 3.4 seconds, and we have to calculate L2. Now, from our discussion, we said period is equal to 2 pi into square root of L over G. Now, to take the square of both sides, we are going to have T square is equal to 4 pi square L over G. And we said T square is equal to 4 pi square over GL. Now, Don't forget, we now say, since this one is a constant, we now say t squared directly proportional to L. So our k will be equal to t squared 1 over L1 is equal to t squared 2 over L2. So k is a constant. So apply this formula now. We need T2. We need L2. So make L2 the subject of the formula. Cross multiply. We are going to have T1 square L2 is equal to T2 square L1. So our L2 will be equal to T2 square L1 over T1 square. So from there we can answer L2 now will be equal to, according to the formula, our T2 is 3.4, L1 is 1.10 meter, then our T1 is 2.0 seconds, 2.0 seconds. 3.4 square and 2.0 square. So our L2 now 11.68 divided by 4.0. So finally our L2 is equal to 2.92 meter. That's example 3. The length of a simple pendulum is 0.36 meter and released at an angle of 10 degrees vertical. Calculate the A, angular frequency, B, frequency of the vibration, C, speed when the ball passes through the lowest point of the swing, G, 10 meters per second squared by 3.142. Now, solution. Now from the question number 1, we are given length of the pendulum. L is given as 0.36 meter. Angle of displacement equal to 10 degrees. So G is given and pi is given. So we have to calculate the angular frequency. That's A, and that is omega. Angular frequency is equal to square root of G over L. Square root of G over L. This one will now give us G is 10, L is 0.36. So 0.36, then that's 10 divided by 0.36. This one will now give us square root of 27.778. Then omega will now give us 5.270 rad per second. 5.270 rad per second. Now, frequency F can be calculated from the angular frequency, which is equal to angular frequency equal to 2 by F. So our F will be equal to omega over 2 pi. Then that one will now give us 5.270 over 2 multiplied by 3.142. So this one will give, this one will be 5.270 divided by 6.284. And our F will now be equal to 0.836 amps. The next is speed, which is equal to square root of 2gs. That when we pass through the lowest point, and G is given, but S is not known. But we can calculate S from our drawing the other time. When you say this is the pendulum, this is the equilibrium position, this is the pendulum as it swings to and fro. This is angle theta, then G is given. This is our S. So from there, if L is given, so we can calculate our S since L is given now by drawing into right angle triangle. This is S, this is theta. So from there now, theta is given. That will be sine. To find S now, to find X, that will be sine theta is equal to S over L. S over L. So our S now will be equal to L sine theta. And what is head given? That is 0.36 multiplied by sine 10. X now is equal to 0.0625. That will be meter according to the question. Now from there we can now find our V now. Now the velocity V is equal to square root of 2 multiplied by 10 multiplied by 0.0625. P now is equal to square root of 1.25, and the final answer for the speed is equal to 1.118 meter per second. Let's take this one as example 4. A simple pendulum has a period of 4.0 seconds. When the length is increased by 1.5 meter, the period is 4.7 seconds. Calculate the original length of the pendulum. Now, solution. Let the original length be L1. Let the original length be L1. So, we don't know the original length, but the period for that original length, let's call it T1 is equal to 4.0 seconds. Then L2 now. L2, which is new length, be equal to L1 plus 1.5 because it's being increased. So, therefore, the period under this one is T2, 4.7 seconds. Now, from our relation, T squared, the relation proportional to L, so we can now have our T squared equal to KL, K now which is constant equal to T1 squared over L1, which is the original length that we need to calculate, which is equal to T2 squared over L2. Don't forget our L2 is L1 plus 1.5. So it will now give us T1 squared over L1 is equal to T2 squared over L1 plus 1.5. So by crossing multiply, we are going to have T1 squared into bracket L1 plus 1.5 equal to T2 squared L1. So let's substitute the value. Our T1 is 4.0 square into L1 plus 1.5 equal to our T2 is 4.7 square into L1. So open the bracket. We are going to have 4 square will be, that will be 16 L1 plus this one will be 24 is equal to 22.09 L1. Collect the like time. This one will now give us 16 L1 minus 22.09 equal to minus 24. So subtract 16 L1 from 22.0 L1. This one will now give us minus 6.09 L1 is equal to minus 24. Minus will cancel minus. L1 will be equal to 24 over 6.09. And L1, which is the original length, will be equal to 3.940 meter. Let's take this one as example 5. A simple pendulum has a period of 17 seconds when the length is shortened by 1.5 meter. Its period is 8.5 seconds. Calculate the original length of the pendulum. You can notice something. That's why I underline it. On the last example, which is example 4, it was increased in length, but this one is shortened in length now. Let's go through this one too. Solution. So let the original length be L1 and the time, which is T1, be equal to 17 seconds. Now, from the question, T2 is equal to 8.5 seconds. Then the L2, since the original length is shortened, that will be L1 minus 1.5. So going by our expression, T square directly proportional to L, so you have our T square is equal to KL. K now is equal to T square over L. Then from there you can now say T1 square L1 over equal to T2 square over L2. And our L2 is L1 minus 1.5. Now cross multiply, we are going to have T2 square L1 equal to T1 square L2. The value of our T2 here is 8.5. And our L1, according to the question, is what we have to calculate. Then our T1 will be equal to 17. That's 17 square. The L2, L1 minus 1.5. So this one will now give us 8.5 L1 be equal to 289 L1 minus 433.5. Don't forget we need to scale this one. Then 8.5 square also will give us what? This one will give us 72.25. So let's collect the like time. So this one will go to 72.25 L1 minus 289 L1, then equal to minus 433.5 equal to minus 216.75 L1, which is equal to minus 433.5. Minus will cancel minus. Therefore, L1 will be equal to 433.5 divided by 216.75. L1, that is the original length, will be equal to 2.0 meter. This is the original length. That is for example 5. Now let's take this one as example 6. The bulb of a simple pendulum of mass 0.025 kg is displaced 0.1 meter from its equilibrium position if the angular frequency is 4.0 rad and assuming simple harmonic motion, calculate the energy of the system. Now, solution. Let's write down the parameter in the question. Mass of the bulb is given 0.025 kg. Displacement S is given 0.1 meter. Then from the question, angular frequency 4.0 rad per second. So we now have to calculate the energy of the system. Normally, that will be kinetic energy, that is KE. That will be half mv square. And from the question, don't forget, for this thing to pass through the equilibrium position, V will be equal to omega x. That's the displacement when S is equal to A. S is equal to A. Now, what is our omega? That will be 4. Our S is 0.1. Then this one will now give you 0.4. So if V is 0.4 meter per second, then we can now say KE will be equal to half into 0.025 multiplied by 0.4 square. So this one will now give us 1/2 multiplied by 0.025 multiplied by 0.16. And if we divide this one will now give us 0.025 multiplied by 0.8. Now, this one is 0.08. Now multiply 0.025 multiplied by 0.08. The energy in the system is equal to 0.002, which is equal to 2 times 10 raised to power minus 3 joule. That's for the example 6. Let's take this one as example 7. And for today, this one will be the last example. Two simple pendula, X and Y, make 400 and 500 cycles, respectively, in equal time. If the period of X is 1.5 seconds, calculate the period of cycle of Y. Solution. We were given two simple pendulum within this question. For y, for x, the number of oscillation is 400. That's number of oscillation for y. For s. For y, the number of oscillation is 500 cycle. For s, the period t, that is ts, is equal to 1.5 seconds. Then we have to calculate the period ty from the question. Now, don't forget, period is equal to, that will be time taken over number of oscillation or cycle. Therefore, t will be equal to tn. And the question says in equal time. In equal time. That is, for ts is equal to ty. Therefore, that will be tx, then number of oscillation of x will be equal to ty equal to number of oscillation of y. And the question asks us to calculate ty. So ty will be equal to ts multiplied by number of oscillation of s over number of oscillation of y. So this one we now give according to the question. That is, ts is 400. Number of oscillation of x, that would be 1.5 seconds multiplied by 400 over number of oscillation of y. That is 500. So from this one, the time taken, the period for y will be equal to 0, we cancel 0. That is 1.5 multiplied by 4. That will be 6.0 over 5. Then ty, that is the period of oscillation of y, will equal to 1.2 seconds. And as I said earlier, example 7 will be the convenient point to stop for today. Don't forget, in the beginning we promised to look at example to illustrate simple harmonic motion. We took 3 examples, but today we were able to look at the first example, which is an oscillation of simple pendulum under simple harmonic motion. So in our next class, we are going to look at examples of another example, which is that of a loaded spiral spring performing simple harmonic motion. And before then, as I said earlier, if you are not joining us, or if you are just joining us, or if you are with us and you've not subscribed, please try to do so. Like, share, and subscribe. So when I post a new video like this, you'll be able to get the update in time. Thank you.